Diamonds and pencil nibs seem like they come from completely different worlds. One is a symbol of luxury and perfection. The other is something we casually sharpen and throw away. But the surprising truth is that both diamonds and pencil graphite are made of the exact same element, carbon. Carbon is one of the most versatile elements in the universe. It sits at atomic number 6 on the periodic table and has 4 valence electrons. These electrons allow carbon to form strong covalent bonds in many different shapes and patterns. This flexibility is the reason carbon forms the basis of life, fuels, plastics, and some of the strongest materials known to science. To understand how carbon creates both diamonds and graphite, we need to zoom into the atomic world. At this scale, the arrangement of atoms determines everything about a material. The ingredient stays the same, but the structure changes the behavior completely. In a diamond, every carbon atom forms 4 bonds arranged in a perfect tetrahedral shape. This creates a 3-dimensional network that extends in all directions. The structure is rigid, tightly packed, and extremely stable. This is why diamonds are the hardest natural material on Earth. The electrons in diamond are locked into strong bonds, leaving no free electrons to absorb visible light. This is why diamonds are transparent. Light passes through the structure and bends dramatically, creating the brilliance and sparkle diamonds are famous for. Graphite, the material inside pencil nibs, has a completely different atomic arrangement. Each carbon atom forms only 3 bonds, creating flat hexagonal sheets. These sheets are called graphene layers. Within each sheet, the bonds are strong, but the layers are held together by weak forces. Because the layers slide easily, graphite feels soft and slippery. When you write with a pencil, thin layers of graphite shear off and stick to the paper. This simple sliding mechanism is what makes pencils work. Graphite also conducts electricity extremely well. Each carbon atom uses only 3 electrons for bonding, leaving 1 free electron that can move across the sheet. These free electrons act like an electrical highway, allowing current to flow. Diamonds, on the other hand, have no free electrons. All electrons are locked into bonds, making diamond an electrical insulator. This difference in electron behavior is a direct result of the atomic structure. The density of the 2 materials also differs. Diamond's atoms are tightly packed in a 3D network, making it denser. Graphite's layered structure contains more empty space between sheets, making it lighter. This dramatic difference in properties, despite having the same chemical composition, is an example of allotropy. Allotropy occurs when the same element exists in different structural forms. Carbon is one of the best examples of this phenomenon. Besides diamond and graphite, carbon can also form graphene, carbon nanotubes, fullerenes, and amorphous carbon. Graphene is a single sheet of graphite and is one of the strongest materials ever discovered. Carbon nanotubes are rolled-up graphene sheets with incredible strength-to-weight ratios. Fullerenes are spherical carbon cages shaped like soccer balls. Each allotrope has unique properties because of how the atoms are arranged. The ingredient stays the same, but the architecture changes everything. Under the right conditions, graphite can transform into diamond. Deep inside the Earth, carbon is exposed to extreme heat and pressure. Temperatures can exceed 1200 degrees Celsius, and pressures can reach more than 50,000 atmospheres. Under these conditions, the carbon atoms rearrange themselves from the flat graphite structure into the 3D diamond structure. This natural process takes millions of years. But scientists have learned to replicate it in laboratories. High-pressure, high-temperature machines can convert carbon into diamond. Another method, called chemical vapor deposition, grows diamonds layer by layer from carbon-rich gases. These lab-grown diamonds are chemically and structurally identical to natural diamonds. They are made of the same carbon atoms arranged in the same lattice. The only difference is how they formed. If diamonds are just carbon, why are they expensive? The answer lies in the geological history. Natural diamonds form more than 100 miles beneath the Earth's surface. They reach the surface only through rare volcanic eruptions called kimberlite eruptions. Most of these eruptions happened billions of years ago. Every natural diamond you see today is ancient, rare, and the result of extreme geological processes. Graphite, on the other hand, forms much more easily. It can form at lower temperatures and pressures and is found in many parts of the world. Graphite is used in pencils, batteries, lubricants, and even nuclear reactors. Its layered structure and stability make it ideal for slowing down neutrons in nuclear reactions. Diamond is used in cutting tools, heat sinks, high-power lasers, and experimental semiconductor devices. The story of diamonds and graphite teaches us something profound about materials. A material is not defined only by what it is made of. It is defined by how its atoms are arranged. A tiny change in structure can transform something soft and dull into something brilliant and unbreakable. So the next time you write with a pencil, remember this. You are holding the same material as a diamond. The universe didn't change the ingredient. It simply rearranged the atoms. And that small change made all the difference. If you enjoyed this deep dive into the science behind everyday materials, make sure to like and subscribe. Tell me in the comments which carbon form you want me to explore next. Thanks for watching.